Okay, welcome to Journal Club, everyone. Today we're talking about Clip, um, probably my favorite network uh, out of all of the networks that I've ever used or that have been trained. But so the paper is titled "Learning Transferable Visual Models from Natural Language Supervision." It's by OpenAI. Of course, these are the authors right here. Um, so let's just jump into what the model looks like. So for anyone who doesn't know, Clip takes in some kind of text and it takes in some kind of image and then it outputs um, two vectors, or depending on your batch size, it could be many vectors, but it outputs a set of vectors. And then using those vectors and this thing called cosine similarity, Clip is basically going to tell us how well these different um, these different text and images match each other. So during training, how that works is it takes in a stack of different texts, descriptions of images, and a stack of different images. And after processing them through a text encoder and an image encoder, it's basically being trained to say, okay, T3, for instance, most matches I3 for another instance. And what's essentially going on is it's saying, okay, out of all of these images that you've given me and all of these descriptions that you've given me, the best match is, this description, and all of the other matches don't fit very well. So they use cross entropy to basically have it pick from a pile of images which one best fits a pile from so it doesn't each to each thing where it's saying, well, this description best matches this text and this one doesn't and this one doesn't, and so on. And so after all that training on a huge data set that they call, let me find the full name, it's like WIT or something. No, WTI, maybe. Let me look. But the point being, after training it on a ton of data in that manner, they're able to say, the model is able to say, okay, this is how well this image fits this description. Let's see. Okay, I need to find, my computer's lagging a bit, but I need to find the data set title because I think it's important to talk about the data as well. Let's see. I remember reading it today. It's somewhere around this area. I just don't remember which page. It's like words and text? Or text and words? I'm just gonna look for a data set. Let's see. Control F is one of the most important. Oh, here we go. I think it's somewhere around here. They create a data set of 400 million image text pairs, which, when you think about it, that's a lot, and so while the architecture is really cool and interesting, the Clip definitely wouldn't be possible without the data that some people, and I don't know if this is the best comparison, but some people think of data as like the fuel to the car that is new architecture advancements. So it's like without a ton of data, you're kind of lost, even if you have this amazing new or interesting way of going about training and architecture. God, where did it go? Where is the title? Well, whatever. But the point being, it's a massive data set, 400 million text image pairs, and those are all used to train CLIP. And they talk about choosing and scaling a model. One thing that they talk about in a different portion of the paper is that with the amount of data they had, they didn't really have to. Oh, here it is. WIT. Why is it not finding WIT in that case? Oh, okay, well. Web image text, yeah. That's so they refer to this data set as web image text, and it has a similar total word count to the web text that they used to train GPT-2. So just like I know I'm kind of belaboring the point, but a massive amount of data was used to train CLIP. Okay. So, talking about the training is fun. Let's talk a little bit more about the architecture. So there's the text encoder, and then there is the image encoder. The text encoder is a transformer. It's, from my understanding, it's a pretty normal, transformer encoder network. It takes text, it maps it using attention to a vector, which I think is pretty standard. The image encoder is interesting because they have a couple of different versions of image encoders. They have, and a lot of you probably know about this because it's a big part of the notebook and something that people have tried fiddling with a lot, which is good. They have the ResNet versions. They have like ResNet 50, ResNet 50 times 4, ResNet, what's the other one? Well, whatever the case, they have a whole bunch of different residual networks, and they have 5 residual networks and 3 vision transformers. Yeah, I know. Like ResNet, not as fun to work with, not as yeah, exactly. It's just not nearly as effective for gradient descent, and I think that's partially just because like it probably focuses more on text, texture within images than the vision transformers, so you get better results when you're visualizing the kind of latent space with a vision transformer. And it's sad, they have these enormous vision transformers, but they haven't released them yet. Who knows if they ever will. I imagine we could, hook up the biggest vision transformer and hopefully see some, improvements over even what we've already got with Big Sleep, Aleph, and the other notebooks that do text to image with that. Okay, so they denote this, let's see. Yeah, so their best model, which they refer to as CLIP, they're using the large vision transformer, as you would kind of expect. And it's trained on GPUs, a ton of GPUs, like look at that. 18 days to train on 592 V100 GPUs, 12 days on 256 V100 GPUs. Just massive amounts of computational power are required. VITL. Yeah, VITL, the large one. I want to mess around with the huge clips so badly. It would be, oh, H is even larger? Yeah, and I guess H is some, they didn't train it for this task, or it was too big. I don't know, but yeah, I want to get my hands on those, but I'll have to wait because who knows if OpenAI will even ever release them. But so the usual way that people use CLIP is they give it a whole bunch of, let me see if I can find an example of this. Yeah, so they give it like a string with a whole bunch of different labels kind of fed in. So like on ImageNet, you would say a photo of a blank, and then you take all 1,000 classes of ImageNet, in fact, let's look at that. Here we go. So you would take all of these classes. So you'd have goldfish, great white shark, etc. And you would say, okay, is this a quail? Is this a peacock? Is this a ptarmigan or whatever? Is this a centipede? Is it a tick? Etc. On and on and on. And you would just feed that into Clip and say which of these descriptions best matches the image. And like that's you know, that's kind of the way that they set it up to be used. So you can end up doing basically ImageNet, but just saying, okay, we're gonna give it text that represents those classes. But the cool thing, what's cool though about Clip, is while you could say, is this a coral reef? You could also say, is this a Pikachu wearing a backpack in the style of Cy Twombly or whatever? And so it's this kind of open-ended, infinitely combinatorial nature of language that makes it more fun. Is it a person? Is it a dog? Is it nothing? Yeah, so you can figure out. You can use it to predict classes, but what's cool is you can also use it to predict, is this, X, Y, Z, whatever. Which I think is something that people are going to start to use to edit data sets really effectively. Is this pixel here? Yeah. Because, you can say, if you're going through a big old data set, you can say, okay, I want to find every dog in this data set, or I want to find every instance of, I'm trying to think of a celebrity, Will Ferrell in this data set. And you can basically say, if it's this confident that Will Ferrell is in this image, then we'll keep the image, and otherwise we'll throw it out, or vice versa. Yeah. And so that's the usual use case. And again, it's very cool, and it does some amazing things, but it's built on these tools that we've had not for a long time, but using ResNet and Vision transformers, which are fairly easy to understand. With ResNet, you're basically using a convolutional neural network. For anyone who has no idea what that means, there are some earlier journal club meetings where we talked a little bit about how it's essentially a filter running over an image, and then a filter again that runs over the output of that filter, and it learns to see different parts of, and it learns to represent these higher order concepts as time goes by. And then the Vision transformer is basically just a convolutional neural network that goes through and takes patches of the image, and then that's used as features in a transformer. And the text encoder is a transformer as well. So it's just this. It's leveraging these cool models, but I think the secret ingredient, the special sauce, is this contrastive learning. That's what people call it when you give it a whole bunch of different options of pairs. In this case, the pairs are descriptions and images, and then you say, okay, which one matches which? So that's contrastive learning, which is a really big deal lately because it's great for supervised learning, or whatever you want to call it, where you don't have explicit set labels for everything. But whatever the case, Clip does some very cool stuff with contrastive learning. Let's see. So I'm trying to think of other high points of the paper that are especially interesting. Let's see, because we've kind of gone over training, we've kind of gone over inference, and the models themselves that are used in Clip. What am I missing? Oh, we should talk a little bit about prompt engineering, because I mentioned it a little bit, how they use, instead of just saying label, with ImageNet, you could say goldfish and see how well it matches how well images match the description. But instead of that, they say a photo of a goldfish or a photo of, whatever it is you're looking for, or whatever many things you're looking for to get ratings of. And in doing so, they get higher accuracy. A label of a label. You could look for, like name tags and labels and kind of get meta with it. That would be fun. Let's see. I'm trying to think of. So they get a higher accuracy by like 1.3% just by using some prompt engineering. I think they talk about this as well, but you could even use multiple prompts and then like average them together, which is smart. It's a good way to do that. Oh, here we go. Yeah, ensembling over multiple zero-shot classifiers as another way of improving performance. By the way, zero-shot classification is basically just saying, okay, we've never seen this image before. We've never even seen this, description before, but we're gonna pair them together. So one shot would be saying like, okay, we're gonna show you one example of something, and then you're gonna one label of it, and then you're gonna start classifying things. Zero shot means there's none of that. You don't use any labels, I guess you could say. How what? Oh, how to average them? So you take the output of the, and I think this is what they're talking about generally, but you take the, let me scroll up. This is a long paper. It's a good paper. It's very long. So you take the output of the text encoder and you give it, Pepper the Aussie Pup, an image of Pepper the Aussie Pup, a photo of Pepper the Aussie Pup, etc. And then you take the output of the text encoder for each of those descriptions, and then you just average across the vectors. And apparently that is very helpful. It's something we could try with some of the notebooks we use. Because, you could say a photo of Abraham Lincoln, a portrait of Abraham Lincoln, the face of Abraham Lincoln, and maybe having all of those texts together and then averaging them would make a better vector to guide, Big GAN or the Taming Transformers VQ VAE. Normalize. Well, so I would just do torch.mean, list of, or torch.mean, and the tensor would be of shape like, in fact, yeah, let's see. So you do torch.mean vector, and you would only take the mean across the 0. Or another way to write this is probably an interesting point, is instead of doing torch.mean vector 0 to take the mean across the 0th axis and saying vector equals, you could also just do it in place and say vector.mean 0. So there are a couple of ways to take the average on certain parts of a tensor, because you could take the average of the whole thing and get one number, but then it's not a vector. If you want to take the average of just a certain part of just a certain axis or dimension of the tensor, then you can say dot mean and specify 0. Or if it's so in fact, this is maybe something useful. If it's an image where it's like 0, 3, blah, 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 let me clean up these commas. 0, blah, blah, blah. Let's pretend this is grayscale and that these aren't all the same numbers, but you could say this is an image, and you could say I want to take the mean across the width. You could just say image.mean 1. And that would give you the mean across 1. There are a lot of, so the way that I think about tensors most of the time is by their shape. And an image's shape is going to be, it's going to have 4 dimensions, and it's going to have a batch size, which is how many images, the number of channels, which is like usually 3 because we have red, green, and blue channels telling us how much of each of those pixels to use, and then you have the width, and then you have the height, or vice versa. Sometimes people do height and then width. But the point being, you could take the mean of that, and you could say, I'm going to take the mean across the batch size, so you get the average of all the images, or you could say, I'm going to take the mean across the channels, so you have all the images, but they all have one average channel now, or you could take it across the height and width as well. But yeah, so that's a little bit about, just kind of a tangent about taking the average in PyTorch. Let's see. So yeah. So for text prompts, that's a good question. So with the text prompts, you feed in, exactly, it doesn't have height and width, it's one dimensional. So you feed in like the dog was Harry, I don't know, and the dog or the photo, the photo of the dog was Harry. That doesn't make sense, but let's just say we want to average those two. They would be spat out of the text encoder as a vector that is of shape 2, and then depending on the size of, depending on the version of clip you're using, I think it would be like 50 or something as the number of numbers that is used to represent each sentence. But so you have 250, and then you say, and that's the shape of it, which would look like 2 lines of numbers, which are both 50 numbers long. So in fact, let's do an example of how that looks. So you have 2, 5. So you would have 2, meaning there are 2 lists, and the lists are right here. And then you have 5, meaning there are, if I can count, meaning there are 5 numbers. Yeah, well, it can be 43. So you end up with something that looks like this when you actually look at the tensor, where it's 2 vectors, and vector just means list of numbers, at least when I'm talking about it. 2 vectors, and they are in a matrix, which is just like 2 dimensional tensors. And a tensor, there's a ton of language here that is not very accessible, but a tensor just meaning anything that you can represent as a shape, as a shape with like dimensions in it, you know? So 2, 5, and let's say you want to take the average of the prompts, so you would just say that tensor dot mean 0, because this one is the 0th dimension, because Python always starts at 0 instead of 1, and this one is the first dimension because again starts at 0. And so you want this dimension to stay. You still want to have 5 numbers because you want to keep the representation and just get the average of the 2. So you just take the tensor, the mean, across the 0th dimension, the 2. So that'll average those 2 vectors, lists of numbers, together. And you shouldn't name anything tensor. You should really name, we should name the tensor something like text encoded. Or you can name it something zany, like I always do in my code, and say like it's Mammy or something. But yeah, so that's how you might do some prompt engineering / like ensembling to get better vectors. Let's see. I should have sent those. Like into the chat. I can do that. Let me get some of this. Or maybe you meant something else. Oh, cool. Yeah, it gets weird when you start to get like 5-dimensional tensors or like 10-dimensional tensors, because some people draw tensors. Like you can draw this kind of thing as a square. Well, not a square, a rectangle. But once you get to a certain point, it's like you pass through 3D space and you're like, well, how do I represent something that's in 5 dimensions, you know? Cool. Prompt engineering, that's a very useful, practical thing to know about. They do a ton of benchmarking, which is good. You know, you want to show that you're actually contributing to the literature and actually doing something. And I think they decide that, like, hey, by the way, if we just had more compute, we could make even better models using this, which is cool. And which seems to be the case. It looks like a lot of things scale with more compute. But yeah, that's just a cool thing. I like Moco. Moco came about before Clip and was like momentum contrastive learning or something. It was cool because it kept like a dictionary of different vectors to be compared. Anyways, that's totally not related to. Well, I mean, it's related to Clip, but totally a tangent. Just a kind of cool approach from a relatively long while back. Let's see. What else do we want to talk about with this? They talk about like how well it generalizes, and that's cool. Let's see. New benchmark testing these systems has found their performance to be much lower than both their ImageNet accuracy and human accuracy. A common theme of proposed explanations is that deep learning models are exceedingly adept at finding correlation in patterns which hold across their training data set and improve in distribution performance. But a lot of these patterns are spurious and don't hold for other distributions. So there's this problem in machine learning where we'll be like, we want to maximize how well we do on one data set. And so they'll pick up on little things in the data set that aren't actually meaningful, these machine learning models. So it's good to show that they generalize to different data, because that's a huge issue. Look how high up their hateful memes is. Oh yeah. Yeah, the hateful memes thing. I don't know if they trained on it. I'm sure they tested on it. And it is, yeah. We could talk forever about how awful the bias is in Clip. In fact, that I love talking about that kind of thing because it's a hard problem because we want to make these really cool neural networks that can, predict anything using web data, and then it's like, oh no, they're as awful and racist and sexist and homophobic and ableist as all of the, worst people online. Yeah, I mean, sometimes it's sometimes it's a downer to talk about because we've got to either find ways to use less data, or we've got to find ways to use data that is no matter what data you're training on, there's this really cool talk by Alison Parrish. Shit, I gotta find it because this is so good. Programming is forgetting. Yes, okay. So let's see what Alison Parrish. Alison Parrish is this really cool. I guess I don't know, poet and also like really technically fantastic in terms of knowing how to use neural networks and all that. So just really impressive woman who has written about this kind of thing, and I would encourage you all to read this. It's called Programming is Forgetting Toward a New Hacker Ethic. Anyways, it talks about how when you program things, you're creating a sort of model of the world, and every model of the world is intrinsically forgetting parts of the world because it's a simplification in a way, or something along those lines. But I've thought about that a lot with respect to data, where your data is never going to capture everything about the world, so you're always going to have data that is flawed. And further, even if the data captures the whole of the world, you're capturing a world that is already biased, you know. So I think it's this really difficult problem where we want to use data to inform our decisions, but we want to use data that is not biased, but we live in a world where if you're collecting data, it is intrinsically biased because the world is biased, you know? So there are a lot of people who are like, oh, we can just use machine learning to decide who gets the job or who, you know, XYZ because it's objective. And it's like, no, machine learning's not objective. It's going to use things like GPA. It's going to use things like SAT, and it's going to pick up on these biases that are intrinsic, well, not intrinsic to the world that we live in, but are really deeply embedded into the world that we live in. And that's just a huge problem because algorithms can obviously be biased in very obvious ways, but they can also be biased in more insidious ways where they, like, you know, pick up on things that are caused by systemic racism and things like that. So that's kind of a good thing to talk about often, that these models should not be used for many different things. There are many ways that they could have, you know, horrible effects. In fact, yeah, I mean, it's true. It's like how our minds work, and it's definitely true that, like, our minds themselves are also prone to similar biases. Like there's like the implicit association tests, the IAT, which can show that, like, yeah, humans even in ways where they're not consciously trying to be biased can have these implicit biases that make them act differently depending on who they're, you know, directing that action towards. Yeah, I don't know. I know that there's definitely this tendency for our brains to use heuristics, these little, like, tricks to get by certain things. And when we do that, it can often, you know, draw on stereotypes and things like that. There's just a massive literature in social psychology examining how people can be biased even if they're not explicitly trying to be. And so yeah, there's definitely yeah, it's a double-edged sword, but it's unfortunate because when we take these shortcuts, and some of them are, you know, less bad than others, but whenever we take shortcuts, we and you know, build a model of the world in our brains, we're forgetting some things and we're inheriting biases that we, you know, from the world and from, you know, the nature of shortcuts that are not always useful. Yeah, I mean, science can do some things, but I think that it's difficult because even knowing that you're biased and even doing your best not to be biased, there's still and I'm not trying to be a fatalist. I think that there are interventions that can help with bias, but you know, I'm not a my area is in social psychology, so I honestly am not the expert on this kind of thing, but it's definitely the case that humans are biased, algorithms are biased, and we want to try to live in a more just world where we try to mitigate the consequences of those biases, and especially when it's, you know, like let's see, there was a paper going onto my twitter.com. Funny, you get to see all of my searches now. Great. Where I mostly look for my own art because I lose it on Twitter. Yeah, no, I agree. Science is I like science. There was a recent attempt at making a I'll find it. Janelle Shane was talking about it. So let me look at that. Yeah, so there was this recent attempt to make an AI chatbot that people would prefer as a conversation partner over people. And naturally, it went terribly wrong because, again, not only are a lot of algorithms trained on bad data, it's also like a lot of people don't care to understand that, like, their models also have privacy issues or will have they'll have these terrible, responses to different. It's one of those things where if you train, it's a good point. People are bad data in a sense, in that if you train on a corpus of data and you're not very, very careful, your chatbot will tell people to kill themselves and all of this other awful stuff. So I think that deploying these models is very hard, and I think that there's at the very root of these models a lot of bad stuff. Let's see, what was I? Oh yeah, we're still reading Cliff, but going off about the biases in it. The primate. Yeah. Let's see. So they compare to human performance, and it looks like they do way better than humans on some tasks at classification. Let me look though. We see that the hardest problems for CLIP are also hard for humans. To the extent that errors are consistent, our hypothesis that this is due to at least two factors: noise in the dataset, yeah, and out of distribution images being hard for both humans and models. Oh yeah, so I guess we're not at superhuman yet, but still pretty cool. Wait, their accuracy though. Zero shot human had an accuracy of 553.7. Yeah, so I read most of this, but I kind of skimmed over the benchmarking. This is cooler than benchmarking, but let's see. Was that the human workers? Let's see. Oh, so yeah, part of it is that they have like dog breeds and things that they're looking at. So yeah, so humans are actually not that great at classification sometimes. So it's interesting that you have to show them some examples of the class that they're looking for them to be pretty good. Yeah, VITH gets 99% on flower benchmarks. Yeah, I'd imagine that especially with VITH, it would be. Yeah, I imagine that it's an improvement over, because I mean, just bigger is apparently better. Yeah, millions of types of flowers. I think, yeah, I haven't looked at the flower data set, like maybe the Oxford one, but I think they usually cut up and select a couple of different types of flowers as classes. I'm not sure though. A concern with pre-training on a very large internet dataset is unintentional overlap with downstream evals. So they were worried that they might have, when they look at ImageNet or something else, some of the images in ImageNet already in the training data. So I mean, yeah, and they look at that. I guess they try to make a data set that definitely was not within the data set that it was trained on, but it doesn't seem to impact performance that much because it's like, a drop in the bucket compared to the training data. Let's see, limitations. Let's see. YTC. Yeah, I bet they benchmarked CLIP on these data sets. Yeah. There are a lot of interesting specialized data sets. Like there's the bird one called Coco or something, and I think it comes with labels of the birds. But it's cool that it's not just massive data sets, it's also kind of specialized ones. Let's see, broader impacts, limitations. So they say image text pairs are unfiltered and uncurated. I don't know about that, because they don't have the F word in their tokenizer as a single token, which you'd think it would be. And when I've tried to generate some not safe for work stuff for science, of course, I I have found that using certain words sometimes does not work. So I'm curious. I'm curious to know if they actually tried to root out certain words and exclude them. But I don't know. Maybe I mean these image text pairs are unfiltered and uncurated. They must have done a little bit of filtering if using the F word doesn't produce coherent results, but maybe I'm wrong. I have I have been surprised that people have been doing less looking into bias less looking into bias lately than I would hope with the visualization stuff. But I think maybe that neuron paper, the microscope one, did. I'm not sure. Let's see. Okay. Oh yeah, here we go. They're talking about bias. This is good. Oh, that's cool. So they looked at some face data sets. Yeah, that's all cool. Okay. 4.9 of the images were misclassified into one of the non-human classes we used in our probes. Oh, that's messed up. Male images were misclassified into classes related to crime, as compared to 9.8% of female images. Interestingly, they found that people aged 0 to 20 years old were more likely to fall under crime-related classes. Yeah, I think that's really interesting. It's interesting that they've looked at things like which people are thought of as by Cliff as being more likely to be criminals and all that. Well, yeah, I've tried doing like tasteful nudes with Cliff, and it does way less well than clothed people. So it is interesting, you know. Yeah, so class design has the potential to be a key factor determining the model performance and unwanted biases. Yeah, that's interesting. Yeah, I think that it's interesting how older people are. Yeah, that is interesting how younger people are thought of as more likely to be criminals. Yeah, interesting stuff. Let's see. And now they're talking about how like most neural networks have these biases and all that. It's like, yeah. Surveillance. God. Oh, cool. So it looks like it's bad at doing small objects in image sequences. Speaking of, I'm wondering when Frozen in Time is going to come out. I want to use that video transformer so badly. Well, I mean, I think that the models are part of the problem because even though it's definitely like deeper than just the models being biased, I think that like they can reinforce that bias in a lot of ways. But I mean, it does start with humans, like most things, where like most bad things. Let's see. Identifying potential beneficial downstream uses of models, surfacing tasks with significant sensitivity, characterizing models in general, creating suites of tests to evaluate systems like CLIP. Kind of cool. If the model said that all people were elected, it would be lying. Yeah, no, I agree that it's like the models shouldn't be told to lie. I just think that it's unfortunate that people will trust the models in such a way that they end up reinforcing biases, because like there are people who use models for facial recognition to see like, oh, is this person a criminal, and of course that differentially harms minority communities because the models are just awful at identifying who people are. Yeah, I mean, down with not to be that guy, but corporations are bad in many cases. Yeah, I feel that. Let's see. Clip is related. Focusing on learning via natural and is not densely connected with a joint. Yeah. Oh yeah, I absolutely agree. Using it for surveillance or for deciding who gets jobs is just messed up. I mean, and people are like, well, it's just numbers, and it's like, no, surveillance and most things where a model interacts with human participants are gonna be bad. Like it's just like I feel like as a person who works with neural networks, I would not want it would be very difficult to work with neural networks that interact with humans in any direct way, because you know you're gonna end up screwing things up, and or the it's just one of those things where we're at a point where the tech is so when a neural network fails like in a very significant way, the you don't find out that it failed until you have really screwed over a lot of people. Like with the and I mean it's one of those things where this happens even with symbolic programming, where it's like if else, like you can make a bad program using if else statements to harm people. um and the difference with neural networks is, of course, when you do that, you're not using if else statements, so it's less explicit, and you end up trying to sneak through these issues by being like, well, it was, or people, often say, well, it was the model that did it. And when we say it was the model that did it, it's like, well, it was also the person who trained it, the people who deployed it, all of that. So yeah, it's one of those things where you have to not trust it like you wouldn't trust some random person on the internet in a way. Um, let's see what else is there in here. I mostly look for figures, pretty figures. Let's see. I think are they using ggplot, or are they using? They're probably using matplotlib, but I'm not sure. Hard to say. I'm trying to think if there's anything else that we haven't covered that's especially interesting. I kind of skimmed the last part just because I haven't had a ton of time this week, but yeah, I'll leave this open in case people have questions about it. But I've mostly covered all of the high points that I thought were best to go over. I think for art and general education, for fun, it's great. They should put more. Oh yeah, I think that machine learning for art is some of the coolest stuff in the world, and I'm biased because like that's what I do in all of my free time. But it really is one of those things where it's like maybe we just should not even bother, trying to use machine learning yet for things outside of. I do so many Starry Nights and Mona Lisas. I'm self-aware enough to know that it is embarrassing how often I just throw Starry Night or Mona Lisa into things. But it's like it's funny if you're trying to reach like a general audience. It's like, who do they know except maybe Picasso, Van Gogh, and Da Vinci? Yeah, well, yeah, it is the industry standard, and And for a while it was like, okay, we're gonna use politicians' faces, and I was like, well, that's fine, but it's not pretty, you know. Even though some politicians look good, it's like I would much rather look at a Starry Night than, yeah, than Elon Musk. I never want to look at Elon Musk unless I'm making mean uh, tweets about him. I think I mentioned on the Discord, but I have some Elon Musk content that is very messed up that I posted on Twitter, and people thought that he was like huffing Mars, but that was not Mars. That was, you know, poop. But yeah, it's yeah, I get tired of seeing pictures of Elon Musk generated with neural networks. Like, even if he notices you, it's like it's not worth it. I don't wanna talk to Elon Musk. Which I'm sure is alienating to like a lot of people, because a lot of people like Elon Musk. I just think that if you have followed Elon Musk's Twitter for long enough, you should know that he's kind of an asshole, to be honest. Things that are popular are never good. I mean, a lot of things that are popular aren't good. I'll go that far. Oh, God. I'm not going to go to Twitter and look up stupid tweets that Elon Musk has made, but this is the same guy who was like, oh, yeah, COVID's not going to be a big deal. And it's like, no, it actually was. It has killed hundreds of thousands. But anyways, I'm getting too I'm going too far out there. This is gonna be on YouTube. Oh God. This is gonna be on YouTube, so I'm trying not to. Well, I mean, I'm fine with alienating people who are fanboys or fangirls or fan people over Elon Musk, but I don't want to go too far. I don't. I don't want Elon Musk to snitch on me and get me fired or something for not liking him. God. Um, Oh, the appendix. I totally forgot that they have this. Let's see if there's anything interesting in there. So I'll stop. So I'll stop talking about Elon Musk. Clip RN, clip VIT, big transfer. Huh. I don't get how bootstrap your own latent works. I don't think anyone does. Interesting. The appendix often has the dark secret magic. Maybe. I don't know. Oh, cool. What? A photo of a guacamole type of food. Oh wow, I forgot. They do radiology stuff. Holy cow, that's cool. I want to someone on the Patreon is a radiologist, I think, and that is really interesting to me. Like I don't think that Cliff is gonna diagnose tumors like a radiologist would, but it's very interesting to think about like how can we, like the fact that Cliff can figure out that this is not a photo of healthy lymph node tissue, but um, a tumor issue in the lymph node. That's amazing. I mean, holy cow! It's like when I took an image of like where I used to live because I was visiting just briefly, and I fed it into Clip, and I was like, I'm gonna generate using gradient descent these captions, a description of the image. Oh yeah, I'll have to check that out. Because yeah, the fact that Clip knows about science is super cool. But like yeah, so I was in this area that I used to live in, and I was like, okay, I'm gonna see if Clip knows that area. And it guessed wrong about where I was, but it guessed wrong within the state, which I thought was pretty amazing. Like it could tell that I was in Utah. Just the amount of information that's inside of Clip, like if I were on a desert island with nothing but like one program, I think it would be Clip. probably. Let's see. Maybe I can find the DNA video. Oh, this one, yeah. I think I saw this. Oh, I like the noise.
What you are about to see is DNA's most extraordinary secret. How a simple code is turned into flesh and blood. Reading the DNA is reading the gene.
Oh yeah, that's. Oh wow. That
It's
RNA or
unseen
whatever is
and
up in there.
copying one of
That's
the
very
two
impressive.
strands. It's made of a close chemical
Yeah,
cousin of
I'll have to
DNA.
watch the whole thing later, but I think that yeah, Cliff just knows so much. It's outrageous. Okay. So I'm gonna end the recording soon, but I'll stick around for like 10 minutes probably. Just for kicks. But yeah, that was a fun journal club. I will let's see. I will upload this to YouTube. I never edit them, so people will have to hear me talk about Elon Musk. But yeah, thanks everybody for coming. That was good.